Hello everyone. Let's solve the third set of the 5 organic questions from JAM 2022 question paper. So the first question in this set is a reaction of 2,4-dinitrofluorobenzene with hydrazine produces a yellow-orange solid X, which is used for identification of organic functional group G. So basically they want us to find out what is G and what is X. So yellow orange solid, no, generally when we think about it, this is generally it is we talk about phenylhydrazine, which reacts with aldehyde or ketone carbonyl group to give you hydrazones, which are azo dye, which is again yellow orange compound. Okay, it's a precipitate. So let us see, the first reaction it says is you are reacting 2,4-dinitrofluorobenzene. So this is fluorobenzene, you see at position 1, which we consider as position 1, this is fluorobenzene. At position 2 and 4 you are having nitro group. So reacting it with hydrazine. So hydrazine, you can see it has nitrogen as nucleophile. Nitrogen is a powerful nucleophile because nitrogen is not very electronegative as oxygen, so its lobe is much bigger and it is happy to give the electron and undergo nucleophilic substitution reaction. But what happens here is generally this nucleophilic substitution reaction is not possible in aromatic ring because aromatic ring has lot of electron cloud around it because of this 6 pi electrons are there, so it doesn't allow nucleophile to reach here. But in this case it will happen by the mechanism what is called as SNAR, nucleophilic substitution aromatic reaction, because two withdrawing groups are there. Nitro is a very powerful electron withdrawing group through minus R effect, and fluorine, and fluorine also creates a lot of positive polarity because fluorine pulls away electron from the benzene ring. This nitro also pulls away electron from the benzene ring, therefore hydrazine can attack. So you can see first hydrazine goes and attacks here on the ring where fluorine is there, and the lone pair gets stabilized over first nitro. Then you can see it gets stabilized by this nitro group, then it comes down, then it gets stabilized by this nitro also, and then this goes back, finally fluoro leaves and you are getting this. So 2,4-dinitrofenylhydrazine is your X, and then this will react with your carbonyl compound to give you yellow dye, which is called as azo dye, right? So this is the carbonyl group which will react with it, and then it forms what is called as hydrazone. So this H2 is there, this H2 reacts with this organic carbonyl compound, and this H2O is lost, and then you get a double bond here. You can see here NHN. So H2 and O is lost, this double bond is intact, so N double bond, and this is the form. This is hydrazone, which is yellow dye, right? So the compound is carbonyl compound. So let us see the options. So options are X will be this compound phenylhydrazine. So this and this A and B are the possible choices, but at the end it is not carboxylic acid. Answer is aldehyde because aldehyde is a carbonyl compound. So our answer is option B. Let's move to the next question. The next question says, among the following compound, the reaction or the reactions that favor or favors the formation of product at 25 degrees Celsius is or are. So all 4 of them are equilibrium reaction. So basically what we are expected to see is which is favorable, which favors the forward reaction and which favors the backward reaction. Because it's tough to say that which will be favorable at 25 degrees Celsius unless you do a reaction and find out. So basically it is it wants us to know, it wants to test us that do we understand which reaction is favorable, forward direction or the backward direction reaction. So let us see the first molecule, first reaction. First reaction nothing but transesterification. You are having a ester which you are reacting with another alcohol, which leads to formation of the another ester, and one of the alcohol gets out and the leaving group goes out as alcohol. So here it goes out is phenol. So you can see here in the forward direction you are having alcohol. Alcohol is a good nucleophile compared to here. You see in the next step in the reverse direction you are having phenol as the nucleophile. Now phenol is not as good nucleophile as alcohol. Why? Because here the lone pair of electron of oxygen is getting delocalized over the benzene ring. So the oxygen loses electron density. So its tendency to go on attack on carbonyl will be much lesser. So it's a weaker nucleophile compared to this. So this looks more favorable to me. Apart from that, what you see is once this goes and attacks, what comes out here? You get what comes out here is a phenoxide ion. And that phenoxide ion will take proton from alcohol to become phenol. Now phenoxide ion is a very good leaving group. Why? Because phenoxide ion is stable. You are having this benzene ring, on that you have O minus. You have this O minus. This O minus you can see is stabilized over the benzene ring, so quite stable. So it is happy to leave. So this reaction is quite favorable. Whereas here the leaving group is ethoxide, methane, ethane, propane, propanoxide ion you can say. So you are having alkoxide ion, O minus ion. This is quite unstable because you have plus I effect by the 3 CH3, CH2 and CH2, this alkyl group, and so makes it unstable. So definitely forward reaction much more favorable than backward. So A is one of the answer. You can see I have shown you the phenoxide ion stabilization, whereas not here. Let us see the option B. Option B is amide formation from ester, that is forward reaction, and backward reaction is from amide. From amide you are forming ester. So nitrogen, again, this is a much powerful nucleophile, cyclohexylamine, because nitrogen is there. Nitrogen is less electronegative. It is happy to donate its electron. Whereas in the reverse direction you are having alcohol. Alcohol is not a very good electron donating group, is not a very strong nucleophile, because oxygen electronegative, so it holds electron very close to itself. So its lobe is much smaller, whereas nitrogen lobe is much bigger. So nitrogen is very efficient in giving its electron, whereas oxygen is not. Apart from that, you see the leaving group here. The leaving group here is alkoxide ion, right? Alkoxide ion. This is stable to a certain extent because oxygen has negative charge. Oxygen is electronegative, it can stabilize the negative charge. Whereas here, if it attacks, if the oxygen attacks here, so this goes up, this bond comes down, and what will go out is cyclohexyl amine anion. Okay, so you get something like this, NH minus. Now nitrogen cannot stabilize negative charge as much as oxygen can stabilize, because nitrogen is less electronegative. Okay, so therefore this is definitely more stable. And the third point what you have to understand is amides are much more stabler than your ester. Amide is tough to break. Even hydrolysis is much tougher, because see, nitrogen is less electronegative. It is happy to give electron. So lot of resonance exists here. So lot of carbon nitrogen double bond exists. Whereas here oxygen, carbon oxygen double bond is not there. It's much lesser, because oxygen is not ready to give its lone pair as much as nitrogen ready, again because of electronegativity. So very clearly forward reaction is more favorable than backward reaction, and therefore B is also the answer. It will be favorable at 25 degrees Celsius. Here what happens? So here you are having HCl. So HCl first proton, this is acid, so proton will be taken. Imagine, let's see what if oxygen takes proton. You get here and you get positive charge. Then you can say, okay, this is quite positive, this is quite electrophilic in nature, then Cl minus will attack. Now Cl minus is a very poor nucleophile. Okay, Cl minus is very poor nucleophile, and what we leave is again cyclohexyl aminium ion, which we saw some time back. It's a very unstable leaving group. Nitrogen cannot stabilize negative charge, so this will not go out. And that too, nucleophilic reaction on amide is very tough. Amide, as we saw just now, it has lot of double bond character. So if you think that such a weak nucleophile like Cl minus will come and attack and will make this group leave, then that will not happen. very tough to carry out this reaction even under high temperature and pressure. Whereas this one is very simple, very reactive. This is acyl halide, very reactive species. This is a good nucleophile. Just now we talked about this because nitrogen has lone pair electron. It is happy to give, and interesting part is this goes up, this comes down, and Cl minus is a excellent leaving group. Cl minus is an excellent leaving group. It's quite big in size, so negative charge is delocalized, and therefore this reaction will be favorable in backward direction, not forward direction. Last step is hydrolysis of this amide in presence of water. Amide, as we said just some time back, amide will have a lot of double bond character. For hydrolysis you will need strong base, something like sodium hydroxide, potassium hydroxide, concentrated, and you have to heat also, heat to boiling. So this reaction looks tough to me. Let us look at here. So here amine will go and attack on this benzoic acid, and this will this OH minus should leave. Now this looks very tough to me. Okay, this looks very tough to me because OH minus is a bad leaving group, but both of them are very tough. Yeah, so basically what I have written there is both of them are tough, and so we cannot say either of them which is possible at 25 degrees Celsius. This reaction is very tough in backward direction because OH minus is a very bad leaving group, but we can think of something like this goes and attacks here, and this once it OH minus comes out, takes proton and goes out, but still it will be tough, but to a certain extent it will be possible, and forward action is almost not possible at room temperature. Definitely room temperature is not possible, and that too with water, not possible with OH minus at higher temperature. So the answer will be option A and B. Let us see at the next question. Among the following, the correct statement or statements is or are: the pK of malonic acid is lower than pK of acetic acid, while its second pK is higher than pK of acetic acid. Then it says the first pK of malonic acid is higher than pK of acetic acid, while the second pK is lower than pK of acetic acid. So no need to read about the four choices. Basically, let us see what is the pK trend. First we should know, because they are not given the structure, we should know what is malonic acid and what is acetic acid. So acetic acid, I hope everybody knows. So acetic acid is a carboxylic acid. So on a carboxylic acid, that is C double bond OOH, if you put CH3, then it is acetic acid. So CH3 is always aceta. It's a common name. If H would have been there, forma, then formic acid. The acetic acid. Malonic acid is a dicarboxylic acid, as it says also, pK of first and then pK of second. So there is a small formula which you can remember. That's how I remember. Ohm's gap. Ohm's gap, right? So Ohm's, O is oxalic acid, M is malonic acid, S is succinic acid, G is glutaric acid, A is adipic acid, P is palmitic acid. So oxalic acid, dicarboxylic acid, which has 2 carbons. Malonic acid is also dicarboxylic acid, which has 3 carbons. Similarly, succinic acid will have 4 carbons, glutaric will have 5, adipic will have 6, and palmitic will have 7. So M will have 3. So let's make it. So C double bond O, C double bond O, I would have drawn, let us see here. Yeah, this is malonic acid. So C double bond OOH, CH2, COH. Now let us find out pKa. pKa, so you understand, higher the Ka, lower will the pKa. Higher Ka means how acidic it is. So if acidity is more, how easy it is to remove. So that means Ka will be higher, that means pKa will be smaller. So for malonic acid, if you remove the first proton, you get negative charge. See, this negative charge is of course stabilized by this resonance. Apart from that, it gets stabilization by the C double bond O, because C double bond O is the electron withdrawing group. Even this oxygen is there, they all will pull electrons, so it will stabilize. So it will be very easy to remove this proton. right? Whereas if I compare with carboxylic acid, once you remove this proton, this negative charge, it is getting destabilized by the plus I effect of CH3. So it will be tough to remove this proton, because the species which is getting is not as stable as this one. Because if you remove this proton, species which are getting is getting more stabilized. See, they are destabilization because of negative charge. This negative charge is making unstable. If you are able to remove this negative charge, it will become more stable. So this COH will be able to pull the negative charge, which will make it more stable, right? So certainly pKa of first pKa of malonic acid will be lower than acetic acid. But second, what happens? See, once you remove a proton, to remove the second proton is tough, because this negative charge and this negative charge, they will be quite close to each other and they will make both of them unstable. So the second pK will be much higher than that of your acetic acid. So the option is, looks like I've forgotten to write the option, but we can easily find out. So the option is the first pK of malonic acid is lower than pK of acetic acid, that is 2. Just now we saw first pK is lower, that means Ka is higher, so it is more acidic. First, it is easier to remove the first proton from malonic acid, while the second pKa is higher than pK of acetic acid. So option A is the right answer. Okay. Yeah, moving to the next question. The compound or compounds that participate in Diels-Alder reaction with maleic anhydride is R. So Diels-Alder reaction, you know, Diels-Alder reaction is 4+2 reaction. You have a diene and a dienophile. So diene is alkenes, two alkenes which are conjugated, and then you react with another alkene. So this is called as dienophile. Dienophile means who loves diene. So simple alkene is dienophile, and simple alkene is dienophile, and diene is diene, conjugated diene. So they go and react. So it's a concerted reaction, very important. It all happens in one step. So what is important is this diene should be cis diene. If they are opposite, imagine something like this is there, something like this is there, then it cannot do gymnastic in one step, that this will go on attack here, this comes here, and this goes here. It needs to be in two-step reaction for this gymnastic to happen. So therefore what we need is a cis alkene. So very clearly option C can be removed, because you can see here it's a logged system, bicyclic system, and it's a trans alkene. Now what happens to this? This is an anthracene system. Okay, 3 aromatic rings are there. Now because of 3 aromatic rings conjugation, lot of aromaticity is lost, and they can act, actually this alkene, they can act as separate alkene, and they undergo addition reaction. See, Diels-Alder reaction is an addition reaction. If a system is aromatic systems don't undergo Diels-Alder, do not undergo addition reaction. They undergo what is called as substitution reaction, electrophilic substitution reaction. But here it can undergo, because such a big ring is there, that aromaticity is reduced, and so it will undergo Diels-Alder reaction. This is a furan. Furan also undergoes, because this looks like aromatic, and it is aromatic to a certain extent, because to have 4n plus 2 electrons, the lone pair of oxygen also needs to be involved. So it is 2 plus 2, 4 plus 2, that will give you 6 electron, that follows 4n plus 2, that is Huckel's rule. And so the system is aromatic. But the thing is, oxygen is not very happy to give its lone pair of electron. Why? Because oxygen is electronegative, hold its electron closer to itself. And so what happens because of this? And because of this, oxygen, this is much less aromatic, and therefore they undergo certain addition reactions, and Diels-Alder reaction is one of them. And this we said no. This is quite aromatic, because nitrogen is there. Nitrogen, we saw a few examples just now. Nitrogen is not very electronegative, so it does not hold electrons very close to itself, so it happily donates, so that all the electrons take part in conjugation, becomes aromatic. So once it is aromatic, it will not undergo addition reaction, it will undergo electrophilic substitution reaction. So the answer is for your question is this will undergo, this will not undergo Diels-Alder reaction. This will undergo Diels-Alder reaction, this will undergo Diels-Alder reaction. So A and B are the right choices. And one more thing, what is maleic anhydride? So you should know what is maleic acid and what is fumaric acid. So they both are carboxylic acid, and this is your maleic acid, okay, cis dicarboxylic acid, okay, and fumaric acid is geometrical isomer of it, and this is fumaric acid, trans dicarboxylic acid, COH. So because it is trans, fumaric acid cannot form fumaric anhydride because they cannot react, it cannot do this much gymnastic and form ring like that, but they will happily undergo dehydration to form anhydride, and that is what is maleic anhydride. Maleic anhydride is like this. Okay, moving on to the next question. Among the following, the suitable route or routes for the conversion of benzaldehyde to acetophenone is R. So we have to see by which all possible ways can we make from benzaldehyde to acetophenone. So first we should know what is benzaldehyde. Benzaldehyde means benzene. On that we are having a aldehyde. Okay. Next is acetophenone. So it's a ketone. Aceta means CH3 will be there. Phenol means phenyl ring will be there. So this is your acetophenone. Okay, this is your acetophenone and this is your benzaldehyde. Okay, let's go option by option. The first, it says you are having benzaldehyde and you are reacting with CH3COCl in presence of AlCl3. So it's a Friedel-Crafts reaction, and CHO we know it is an electron withdrawing group, so meta directing, it will give you formation of this product. At a meta position you will get COCH3. So this is not what we expect. Option B, what it says, it's a quite a few steps. So first they are reacting it with propane 1,3-dithiol along with Lewis acid, that is BF3 Et2O. Then second step they are using a very powerful base, that is N-butyl lithium. Third step methyl iodide, and then HgCl2, Hg2 plus it is, and CdCO3 H2O. So let's see. So first when you are reacting it with dithiol, propane dithiol, 1,3-dithiol, what it does, it forms thioacetal. Okay, so it goes like that. So H2O is basically lost, this H and this H along with this oxygen, is lost, and it forms this kind of acetal, thioacetal. Now sulfur has vacant d orbitals, so it stabilizes this negative charge. So if you can remove this proton till now was not acidic. This proton you cannot remove, because if you remove this proton you get negative charge which is not stabilized by any means. But once you form this, then you can remove this proton, because once you get the negative charge, this negative charge is stabilized by this sulfur. This is called Umpolang effect, or reversal of charges. See, initially what happens here, there is a positive polarity. Why? Because oxygen is there, oxygen pulls the electron towards itself, so it has negative polarity, whereas this carbon has positive polarity. So nucleophile wants to attack here, right? And this aldehyde acts as an electrophile. But here, after forming of this thioacetal, now this positive polarity has become negative polarity, right? So there is a reversal of polarity. This is called as Umpolang effect. Now this acts as a nucleophile rather than as electrophile. So this acts as a nucleophile and goes and attacks the electrophile, that is CH3I. So it attacks CH3 and this I minus leaves and you get this. And then this sulfur has very strong affinity for Hg2 plus. So use Hg2 plus and water so that you remove it and you get COCH3. It gets out and you are getting this acetone. Okay. Now that's what the answer. So from aldehyde, from benzaldehyde, you can form acetophenone. So this is one of the option. Second, it says you are having benzaldehyde, you are adding NaNH2 and MEI. So that's what it was trying to see. NaNH2 is a very powerful base. And what it wants to see that, will you get confused? Will you remove this proton by this NaNH2 and then that negative charge goes and attacks Me from MEI and you get this acetophenone? But no. However strong is the base, even if you use the strongest base, that is N-butyl lithium, you cannot remove this proton. This proton is not acidic at all. Okay, this proton is not acidic at all because negative charge does not get stabilized anywhere. So no reaction will happen. Fourth reaction, let us see. The fourth reaction says you are having benzaldehyde, you are reacting with Grignard reagent, that is methyl magnesium bromide. So you know methyl magnesium bromide, the methyl has negative polarity, magnesium has positive polarity. So this Me minus will go and attack here. O goes up, you get O minus, MgBr plus, and then you put aqueous acid, you get OH. Now it is secondary alcohol. So if you oxidize alcohol, secondary alcohol, it forms ketone. So you get acetophenone. So option B and option D are the right choices. That's it for today. Thank you very much.